Hello, AP Physics 2 kids. Today I'm making this video to show you how to derive, let me write this down, deriving Torricelli's theorem from Bernoullis equation. So Torricelli's theorem is something we've not spoken about before. This is brand new to us, but you are familiar with Bernoullis equation. And I'm going to be applying Bernoullis equation to a very specific circumstance. Let's say that you had a trough. And there was some water in the trough. And also there was a little hole down at the bottom of the trough like this, so that water was pouring out of the trough onto the ground. That's the situation we want to look at. We are going to be applying Bernoullis equation to this situation. So Bernoullis equation, just to remind you and set it down, here is the pressure at point 1 plus 1/2 of the density times the velocity at point 1 squared plus the density times the acceleration due to gravity times the height at point 1 is equal to the pressure at point 2 plus 1/2 times the density times the velocity at point 2 squared plus the density times the acceleration due to gravity times the height at point 2. This term here and this term here are kinetic energy equivalents. These two terms are potential energy equivalents. So, because they come from conservation of energy, that's why they bear that resemblance. In order to apply Bernoullis equation here, we're going to have to think very cleverly. It is not at all clear at first glance that you can use Bernoullis equation here. We're going to have to make some simplifying assumptions, and we're going to have to think carefully. Right now, what is the pressure that is pushing down on the surface of the water? That's a question. Also, what is the pressure here? And a lot of kids want to think that the pressure at this point is from the water pressing down, but I want to think about the pressure going in here. Not the pressure going out, but the pressure going in. That would be pressure 2. Because the 2 points I want to look at is at some point along the surface of the water and another point here. You could think of it like there was a pipe that went down into the water like this, and that pipe turned and went like this. So you could think about it that way. Now that's not what actually happens, but you can imagine it being like that. And Bernoullis equation applies to pipes. So you could think about it like there's a pipe here and the water's going along through the pipe. Then the pressure here at this end of the pipe, it's open to the air. So this is atmospheric pressure. PATM, pressure atmospheric. And this is also open to the air. So this is also pressure atmospheric. That's the first simplifying assumption we're going to make. And so if this is the atmospheric pressure pushing down on the surface of the water, And at the hole, we have atmospheric pressure pressing inwards. Does that make sense? Hopefully it does make sense, because air is pressing down on the surface of the water, and then this little hole is open to the air, and so the air is pressing inwards here, because the air can be treated like a fluid in this case, so it can press any direction. And so we've got atmospheric pressure here and here, which means that in our equation, P1 and P2 are equal. So if I were to subtract P2, it would cancel with P1 because they're the same thing. So they're going to become 0. That simplifying assumption is really important. So then Bernoullis equation simplifies down to this. You've had algebra. You're all bright, mathematically inclined people. You should immediately notice you have rho and g are the same on this side and this side, and that 1/2 rho is the same. So the first thing that should pop to your mind is, let's scooch things around and combine like terms, and that's what I'm going to do. Well, not combine like terms, but yeah, get the like stuff together and manipulate. So like this. Wait a second, I've confused myself. Why did I say y here and h here? I know why, but let's call it, let's be consistent. Let's call it y in both cases. Sorry about that. That's confusing, but hopefully that makes sense. If I'm going to call this y1, I should call this y2, y1, y2. So then this would be y2 minus rho g y1. So y1 is how high up you are. So this would be y1, and this would be y2. Now let's pull out the common stuff. So you're going to get 1/2 rho times v1 squared minus v2 squared is equal to rho g times y2 minus y1. You can set the origin wherever you'd like. When you're dealing with heights, it's pretty common to set the origin down near the bottom. So if you set the origin down at y2, that would make y2 0, and then it would be 0 minus y1. So if this becomes 0, because you set the origin, then that becomes 0. And this is going to become negative rho g y1. Now we're going to make the next simplifying assumption. Let me finish writing this out. So this is rho Here's our second simplifying assumption. If you would assume that this is a really big trough of water, there's a lot of water in here, then the water that's shooting out of the hole is going to be a very small amount of water compared to how much water there is in the trough. We're talking about making like a little pinprick hole, a tiny little leak. Not a very big one, a real tiny one, like you just took a pin and poked it in to the side of a horse trough, which you couldn't do that through metal, but if you could. So you just poke a little tiny hole, and the water's going to be squirting out super duper fast, but the hole is really, really tiny compared to how much water is in the trough. The reason that it's important is then the velocity is going to be really big of the water coming out here, but the velocity of the water falling, how quickly will water be falling in the trough? It's going to be super duper slow. If you just got an itty bitty pinprick kind of hole here, then the water level dropping in the trough is going to be very, very slow. So assume that that the water level, no, that the water in the trough has a huge volume, huge. So V1 is very, very small. So we will assume V1 is approximately equal to 0. Is it actually 0? No, but we're going to assume it's super duper small because the water is going to be dropping in the trough very, very slowly, and we're going to assume it's so slow that it's practically 0, and that will help us here. So if we make that assumption, then V1 goes to 0. So with this assumption, we get, and then there's a negative, because you got to multiply it inside, and there's a negative in there, negative . Oh, wow, look at that. Okay, so now I have a negative on both sides, so the negatives cancel out. That's sweet. And look, my rows are on both sides, so you can just go row, row your boat, and that goes away too. So there goes my negatives, and there goes my rows. Then you got 1/2. So if I want to solve for this, the velocity 2, multiply 2 by both sides and take the square root. And this is what we're looking for. This is called Torricellis theorem. If you don't think about it very much, that might be like, okay, whatever, that's cool. But it's actually cooler than you even think. So let's explore what makes this so interesting. I want to remind you back to last year in AP Physics 1 when we dealt with kinematic equations and you dropped a softball or a basketball or something, and you had this equation that remember that equation? So if I freely drop a softball and its initial velocity was 0, then its final velocity is going to be equal to Vf is equal to the square root of 2a delta x. Oh my goodness. Look at that. Look at that. We got the Vf, V2, we got the square root 2. The acceleration when things are dropping near the surface of the Earth is g. 9.8. And the change in my distance is going to be y1, because if I'm going y2 minus, well, basically, since this is g and y1, that's the same as this being a and delta x. That takes care of the sign issue, as long as you remember what it means. This is the same darn equation. So what this means is that if I took a little sliver of water, or a little fluid element, remember we talked about that in class yesterday, what a fluid element was. If we take a little fluid element, a little tiny plug of water, and it was in our great big container. So I had a container drawn over there a couple minutes ago on the other sheet of paper with my little plug of water where the water could go out here. So if my little plug of water, how fast would it be going when it comes out here? It would be going just as fast. This is the height. The plug of water would be going just as fast out sideways as it would go if I just had the plug of water and I dropped it from the same height. Because if I took that plug of water and I dropped it from this height, it would have this velocity. So if I dropped it this distance, it would have this velocity. But that's the same equation as this. So if I took the plug of water and I dropped it, it would accelerate due to gravity's pull. It would have the same velocity downwards, if I just dropped it, as it's going to have sideways if it goes out the pipe. That's really, really cool. So if I just took the water and I dropped it, it would start speeding up and speeding up and speeding up, and it would get to a certain speed at the bottom of my container, and however fast it would be going downwards if I dropped it, then if it were just in the container and it was squeezing out this way, then the speed it would have shooting out would be the same speed it would have if it fell the same amount of height. You might want to practice saying that or thinking your way through it. That's a really cool thing, and that's Torricelli's theorem. All right, hope that helped.